KCET 2026 champions. So welcome back to the Sankalp series, where we have taken a pledge that we will work every single day, put all our efforts to get top 1000 rank in KCET 2026 examination. So in the past few classes we have started the chemical kinetics chapter, and today will be the last part of chemical kinetics, where we will be talking about the effect of catalyst and what is collision theory. Okay, two important but yes, not, I'll say small topics but important topics. Okay, so let us see here. So today's topic I have already discussed. So now let us understand what is a catalyst. Okay, so you have many times heard that particular thing act as a catalyst. So how do we define catalyst? Catalyst is something which increases the rate of reaction without getting consumed or without getting chemically changed. Now what does that mean? Suppose you have a reaction, you added a catalyst. Due to that catalyst, the rate of the reaction increased, and after the reaction the catalyst is remaining as it is or as it was before the reaction. There is no chemical change or no change in the property of the catalyst. Okay, so let us see here. Okay, a catalyst is a substance which increases the rate of the reaction without itself undergoing any permanent chemical change, as I have explained you. Now giving you an example, MnO2 acts as a catalyst so as to increase the rate of this particular reaction, where you have potassium chlorate is getting decomposed to potassium chloride and oxygen, so in the presence of MnO2. Now when the added substance reduces the rate of the reaction, it is called as an inhibitor. Okay, so we cannot call every substance which increases or decreases the rate of the reaction as catalyst. If it is increasing, it is called as catalyst. If it is decreasing, it is called as inhibitor. Okay, now moving to the next, how this catalyst actually work. What is the, how can, by adding a substance the rate of the reaction actually increases. Okay, so for that we will understand one thing from the equation, the Arrhenius equation. What is Arrhenius equation? K equal to A into e to the power of minus EA by RT, right? So can I write this equation like this? A into e to the power of EA by RT. Now let me tell you a scenario. Suppose activation energy is very high. Okay, so what will happen? Suppose for a reaction, what is activation energy? If you have remembered, we have a reactant forms an suppose this is a reaction, this is the energy of the reactant, this is the transition state, and this is the energy of the product. So this energy, right, that is required from the energy of the reactant to the transition state, this energy is called as activation energy, right? Now for example, if the activation energy is very high, okay, this value is very high, then can I say that e to the power of EA by RT will also be very high, because the numerator is very high, this whole value will be very high. So if this whole value is very high, then I can say that K value will be less, right? Inversely proportional, if this term is a very big term, then the K value will decrease, right? Now at the same time, if the activation energy is having a lesser value, then I can say this whole fraction, that is e to the power of EA by RT, will also have a less value, and finally I can say that K will also have a less, if this is having a less value, I can finally say that K will also have a higher value. So what I can say is, if activation energy is less, then the K value will be high. Rate constant, if this is high, then automatically rate is also high, right? So catalyst is the one which plays here. It changes the activation energy of the reaction. It reduces the activation energy of the reaction, and as a result of which the activation energy reduces and the rate constant increases. So how does catalyst do this work? How does catalyst increases the rate of the reaction? By decreasing the activation energy of the reaction. Okay, so that we will see here. Yes, so see, there is a concept that is called as intermediate complex theory of catalysis. Okay, so catalysts work on this particular theory, that is intermediate complex theory. So according to this, what happens whenever a reactant is reacting, whenever the reactants are reacting, they are producing an intermediate. Okay, so forms temporary bonds with the reactant. So what happens? You have given the reactant, catalyst is there. Catalyst forms a temporary bonds with the reactant, okay, and it forms an intermediate, or it forms a transition state which is not very stable. For a temporary time, catalyst forms some bond with the reactant, okay. Next, formation of an intermediate complex, and this results in the formation of an intermediate complex. Next, what happens about this intermediate complex? It is a short time, it is very unstable. For a very short period of time it is formed. Next, it decomposes to give you back the products and the catalyst, okay. So for example, if you see, this reactant is there, okay, and if I add a catalyst here, then what will happen? The reactant and the catalyst will combine to give you an intermediate, okay, and then this intermediate will decompose to give you product and the catalyst back, okay. So effect on the reaction pathway. So what happens when this catalyst finds, or when this catalyst forms a bond with the reactant, what exactly happens? So provides an alternative pathway for the reaction, okay. So see, again if I tell you, suppose I have a reaction A to B, okay. Now without catalyst, the reaction is suppose following this pathway or this mechanism. It is without catalyst, okay. Now the activation energy for this one is E1. Now when you add a catalyst, it follows a different mechanism, okay. It follows a different mechanism with catalyst. The activation energy is different here. So when the reaction mechanism changes, the activation energy will also change. So when a catalyst is added, the reaction mechanism or the reaction pathway is altered, and that is why the activation energy of the reaction increases. If I use the same pathway, then it will have the same activation energy, but our task is to reduce the activation energy, and to reduce the activation energy we have to follow a different mechanism. So when you add a catalyst to the reactant, first of all it forms bond with the reactant, one intermediate is formed, and after that it also provides a different pathway or different mechanism for the reaction. Clear? So now if I understand here that this alternative pathway has a lower activation energy, the goal is to reduce the activation energy, and that is achieved by having a different or an alternative pathway for the reaction. Reduce the potential energy barrier and makes the reaction proceed faster, okay. So that is how this activation energy works. Now I'll give you a diagram here to understand, very important. It is asked in the PU exam also, okay. So the effect of catalyst, if you have to answer, you have to definitely draw this diagram. I'm talking about the PU exams or the board exams. So you can see here that if there is no catalyst, this is the pathway of the reaction, this solid line, okay, and you can see the energy of activation without catalyst is very high. Now when I use the catalyst, the reaction pathway is this dotted line. And when I have this dotted line, you will see that here the activation energy with catalyst is a smaller activation energy. And when I have this one, the reaction, or I can say when you use catalyst, you will have a better rate, because the rate of the reaction will increase. Okay, so this diagram is very important. This activation energy, this is the first pathway with catalyst, its activation energy is higher. We use a different pathway for the reaction whose activation energy is lower. Now when the activation energy is reduced, the rate constant will increase. Okay, now we will have something that is the, okay, here I'll just change, sorry, one second. Yeah, so this is also under effect of catalyst, a slight change in the heading I forgot. So it is effect of catalyst. Now we will study some special features about catalyst, what exactly it does, what it doesn't do. So that all things are very important, and MCQ questions from here will definitely be asked either in your PU2 boards or in the KCET examination. So the first one is, a small amount of catalyst can catalyze a large amount of reactants. So you don't have to add a large amount of catalyst. Catalysts are so powerful that even with a small amount of catalyst, the reaction can proceed and the rate of the reaction can increase. The second thing is, it does not alter the delta G of the reaction. The Gibbs free energy is not altered by putting the catalyst. Why it is not altered, we will discuss about that. Okay, it catalyzes the spontaneous reactions but does not catalyze the non-spontaneous reactions. This is also important. Those reactions which can happen by its own, Okay, for non-spontaneous reactions you are providing an energy, so you don't have to provide catalyst there. But in spontaneous reaction, that reactions are happening by their own, so you need to provide a catalyst so that the reaction becomes faster. In non-spontaneous reaction, already a source of energy is provided, so there we don't require catalyst. Okay. Next, it is also found that a catalyst does not change the equilibrium constant. This is very, very important. Rather, it helps in attaining the equilibrium faster. So suppose I have a reactant like this, reaction like this. Okay. Now this reaction attained at the equilibrium, suppose after 10 minutes. Okay. And the equilibrium constant for this reaction is suppose 10 to the power of minus 11, for example. Okay. Now what I did for the same reaction, okay, for the same reaction I added a catalyst here. Okay. Now what changes you can observe? You will observe that the Kc value is still 10 to the power of minus 11. The Kc value is not changed, but this equilibrium was attained in 4 minutes. Okay, so what does catalyst do? It helps to attain the equilibrium faster, but the equilibrium constant value does not change. What is the formula of equilibrium constant? Concentration of the product by concentration of the reactant, right? Now after 10 minutes, what was the concentration of product and reactant? The same concentration could have been achieved with the catalyst within 4 minutes. So the formula of equilibrium constant is independent of time. So whether it is 10 minutes or 4 minutes, it doesn't affect the K value. The only thing is the product concentration and the reactant concentration remains same. Okay. Now moving to that, it catalyzes the forward as well as the backward reaction towards to the same extent, so that the equilibrium state remains same but is reached earlier. So how does this happen? So the rate of forward reaction, so I'll just use one more time. See, I have a reaction like this. We'll take two cases here. Case 1, okay, there is no catalyst, okay, and I have case 2 where I have catalyst is present. So now suppose here what happened, the product concentration, the reactant concentration is 10 moles and here it is 2 moles, and after it is 10 minutes. Okay, here the product concentration is 10 moles, reactant concentration is 2 moles, but the time taken was after how much? 4 minutes. Okay. Now how does it happen that the rate has been increased but still the K value? How does this product and reactant concentration with catalyst remain same? Why does it remain same? It remains same because the rate of forward reaction and the rate of backward reaction both were changed by equal amounts. Okay, so the forward reaction, if you are increasing, the backward reaction was also increased by the same amount, as a result of which the equilibrium constant remains same. If you remember, equilibrium constant also has a formula of a K forward by K backward, right? Now suppose this is for this without catalyst, it is K forward by K backward, right? One second. Yeah. Now what happens when I used catalyst? Okay, yeah, so when I use catalyst, what is the K forward reaction? K forward reaction became 2 times and K backward becomes 2 times. Now if you take the equilibrium constant formula, it will become Kf by Kb. So the value remains same because both are increased and decreased by the same amount. Okay, so that is why the K remains constant. And now if I talk about this one, that is delta G value, the formula of delta G is minus 2.303 RT log of K. Now the K value, since it is remaining constant with and without catalyst, the G value will also remain same. Now delta G gives free energy value also remains same. Okay. So next we'll do certain 5 questions. Let us see now some quiz. First question, the rate constant K dash of one of the reaction is found to be double than that of the rate constant K double dash of another reaction. So what I say here is K dash, yeah, K dash, okay, of one of the reaction is found to be double than that of the rate constant of the another reaction. So what I can say from here, K dash is 2 times of K double dash. That means clearly I can say that K dash is greater than K double dash. If for example, if I give you 6 is equal to 2 times of 3, okay, then what I can say, this 6 is greater than 3, so K dash is greater than K double dash. Now if I talk about activation energy, the relationship between the corresponding activation energy of the two reactions, so obviously EA dash will be less than EA double dash. Now why is that? We have studied that K, the rate constant, is inversely proportional to activation energy. If rate constant is high, its activation energy will be less, right? So I have EA dash will be less than EA double dash. That is option number B here. Next, we'll move to question number 2 here. For a given reaction, the presence of catalyst reduces the energy of activation by 2 kilocalorie at 27 degrees Celsius. The rate of the reaction will be increased by, okay. So let us see here. Suppose I have for one reaction, suppose K is equal to A into e to the power of minus E by RT, okay. Next, you have for a catalyzed reaction, okay, this is the catalyzed reaction. The rate of the reaction will increase by. So what I can do, from this, the presence of the catalyst reduces the energy of activation by 2 calories. Means I can say that this energy of activation for this one is EA minus 2. Okay, where EC is the activation energy with catalyst and EA is the activation energy without catalyst. Are you getting this one? See, when I used catalyst, the activation energy reduced by 2 from the initial value. This was the initial value EA, or I'll just mention E here. Okay, so this was the initial value. Okay, when I use the catalyst, the activation energy reduced by 2. So that this value is how much? EC should be equal to E minus 2. So now let us just divide this equation. So if I just divide this Kc by K, so when the activation energy is reduced, the rate of the reaction will definitely increase. So I can write this one as A into e to the power of minus EC by RT divided by A into e to the power of minus E by RT. Okay, so that will give me here E into E minus EC by RT. Okay, that is equal to E into, what is this value? E minus EC value will be 2. Okay, E to the power of 2 by RT. So that is option number C here. Okay. Moving to the third question. Which of the following factors are responsible for the increase in the rate of a surface catalyzed reaction? Okay, so surface catalyzed reaction are generally zero order reactions. Okay, so a catalyst provides proper orientation for the reactant molecules to react. Heat of adsorption of the reactants on the catalyst helps reactant molecules to overcome the activation energy. The catalyst increases the activation energy of the reaction. The catalyst never increases the activation energy. So this is the wrong statement. These two are correct statements. So option number B is my correct answer. Okay. Moving to question number 4. When a catalyst is used in an equilibrium process, it increases the rate of forward reaction, it decreases the rate of backward reaction, it decreases the activation energy of forward reaction and increases the activation energy of backward reaction. It fastens the attainment of equilibrium by lowering the activation energy. Yes, so we attain the equilibrium faster than the time required without catalyst. So that is why option number D here. Okay, there is no it increases, decreases, no, it does both by the same amount, and it decreases the activation energy of the forward and increases the activation energy of the backward. That is also wrong. Okay. Moving to fifth one, which of the following statements about a catalyst is true? A catalyst makes the reaction feasible by making G more negative. We have studied that delta G is not affected. A catalyst makes the equilibrium constant more favorable for forward reaction. Equilibrium constant is also not changed here. A catalyst accelerates the rate of reaction by bringing down the activation energy. Yes, definitely correct. A catalyst always increases the rate of the reaction. See, this statement, when we talk about here catalyst, here actually inhibitor is also involved. Okay, if you in majority a catalyst can behave as a inhibitor, or a catalyst may also increase the rate of the reaction, may decrease of the rate of the reaction. The substance, a catalyst which decreases the rate of the reaction is called as an inhibitor. Are you getting? See, a catalyst, majorly it increases the rate of the reaction. There are certain catalysts which decreases the rate of the reaction, and them we call as inhibitor or poison. Okay, so a catalyst can decrease the rate of the reaction also. Such catalysts are called as inhibitors. So that is why this statement is not correct. Option number C is the correct answer. Okay, now we will move to the next topic, that is collision theory. Okay, so how exactly a reaction takes place? What are the is something that collision theory tells us? Collision theory tells us that a reaction can take place only when the reactant molecules collide with each other. Okay, the reactant molecules should collide with each other, but there are certain criteria how the reactant molecules should collide, what should be the energy, what should be the factors that will every collision lead to the reaction or not. So certain things are there in collision theory that we need to understand. So first of all, collision theory considers the reactant molecules as hard spheres. Okay, it doesn't consider the actual structure of the molecule, it considers all the reactant molecules as spheres. Okay, then reactions, according to collision theory, reactions can occur only when the reactant molecules collide. Okay, now there is some term called as collision frequency, which is the number of collisions per second per unit volume. Okay, but if suppose two reactant molecules are there, I have a big container like this. Okay, and there are so many molecules present here. Okay, and suppose this is 1 unit volume. For example, this is 1 unit volume. So in this 1 unit volume, how many collisions are taking place? Okay, so I'll just make it more simple. Okay, so in this 1 unit volume, these two particles, how many collisions are taking place in this particular unit of volume per second? Number of collisions per second per unit volume is called as collision frequency. Okay, next, activation energy, it is the minimum energy barrier. So what happens whenever two molecules are reacting, they must cross the minimum activation energy barrier. Means when they collide, the energy should have at least the activation energy, that much energy they should gain after collision. And then there is another term which is effective collision. For effective collisions, the energy should be greater than the threshold energy. The collision energy should be greater than the threshold energy, and the reactant molecules must collide in a proper orientation. Both of these factors are very, very important. If there is no proper orientation, then also reaction will not take place, and if the energy of the collision is not more than threshold energy, then also reaction will not take place. So both of these conditions has to be satisfied for effective collision, and when there is effective collision, there is a reaction. Okay, so I can draw this flow chart like this. You have effective collisions. Okay, see, effective collisions can give you up reactions. Now, how do I define effective collision? Effective collisions can be defined by where the energy of the collision is greater than or equal to threshold energy. Okay, and there is proper orientation. Okay, so these two factors will lead to effective collision, and effective collision will lead to reactions. Okay, so you can see here another point is their steric factor. So it is not that only means these two definitely will contribute to effective collision, but there is one more factor, that this factor, right, this proper orientation factor is represented by this term P. Okay, in the equations I'll show you. So when we thought that okay, collisions can lead to reactions. There was no discussion about proper orientation. So at that time we have this equation, A plus B is product, and the rate of this reaction can be given by ZAB into e to the power of minus EA by RT, where this ZAB is what? Collision frequency. Okay, collision frequency, and EA by RT is the number of or fraction of molecules. I'll write like this. It is the fraction of molecules having energy greater than threshold energy. Okay, fraction of molecules having energy greater than threshold energy. Okay, if this is there, then that is represented by e to the power of minus EA by RT. Okay, so the collision frequency is there and this is there. Next, what happens? Next is this factor which came as proper orientation. To represent this factor also, we have equation is finally modified, where we have P into ZAB into e to the power of minus EA by RT, where P is what? P is the probability or orientation factor, ZAB is the collision frequency, and e to the power of minus EA by RT is the number of molecules colliding or number of fraction of molecules having energy greater than the threshold energy. Okay, so this is all about collision theory. Now we will do some questions on collision theory. So collision theory is applicable to when two molecules are reacting. So it is always applicable to bimolecular reactions. Okay, next, for a certain reaction, a large fraction of molecules has energy greater than the threshold energy. Okay, that e to the power of minus EA by RT is satisfied. Still the rate of the reaction is very slow. What can be the reason? So we know that there are two important factors. One is the energy, another is the orientation factor, right? So the colliding molecules could be large in size. This doesn't have any sense. The colliding molecules must not be properly oriented for effective collisions. Yes, the orientation is a major factor. They have to collide in a particular direction, in a particular angle, so that the product formation will take place. Okay, so even though here enough energy is there, if this factor is not met, then the reaction process, the rate of the reaction will be very slow. Okay, let's see question number 3 now. For effective collisions, the colliding molecules must have minimum potential energy, sufficient kinetic energy, sufficient potential energy, maximum energy of activation. So we have discussed that these particles should have sufficient kinetic energy. So that is why answer is option number B. Okay, moving to the 4th question. According to collision theory of reaction rates, every collision between the reactants leads to chemical reaction? No, every collision doesn't lead. Rate of the reaction is proportional to velocity of the molecules? No. All reactions which occur in gaseous phase are zero order reaction? This is not like that. The rate of the reactions is directly proportional to the collision frequency. Yes, if you have seen the equation, we have K equal to P into ZAB into e to the power of minus EA by RT, right? So I can say the rate is directly proportional to ZAB or collision frequency. Okay, moving to the 5th question. A chemical reaction proceeds following the formula K equal to PZ e to the power of minus E by RT. Which of the following processes will increase the rate of the reaction? So lowering the EA, so we have already discussed if activation energy reduces, the rate of the reaction will increase. Lowering of P, if P reduces, K will reduce, so that will not increase. If Z reduces, then also K will reduce. Rate of the reaction is independent of all the factors? No, it depends on the activation energy. So we have option number A here. Okay. So students, that was the end of the chapter chemical kinetics. Okay, and I haven't put any homework questions because you have not answered the previous homework questions till now, so I'm waiting for those. And in the next class we'll be solving the previous year questions from the chapter chemical kinetics. So if you have any doubt, put down in the comment section or just go and revise this chapter so that we can solve the questions in the next class. Okay, that's all in this class, students, and I hope you have liked the session. Thank you for watching and all the very best. Keep smiling and keep learning.